Jeff, I think you're going to kick us off.
I am. So welcome, everybody. If you're not sure where you're at Community Development for Open Science, building strong communities around open source software and open science. Part one, we sort of merged our two sessions into two parts. So we're going to be speaking mostly about community development around open source software in part one. And then later this afternoon, I believe at 4 p.m. Eastern, will be community development around open science, which is sort of tangentially related, but we wanted to sort of bring those two groups and communities together to sort of have this open discussion. So again, we're gonna talk about open source software. The presenters are going to be talking about open source software in this session, and then open science in part two at 4 p.m. Eastern. So it'll be great. It would be great to have sort of some continuation of the same participants in that later session. And then obviously, if there's a conversation that we didn't quite get to in the breakout sessions today, or excuse me, right now, we can sort of pick that up a little bit later in the afternoon. And if you scroll down in Kiko chat in the Google Doc that everyone is throwing their information into right now, you can sort of see the seeded questions we've got for the breakout rooms. So I encourage you to sort of look that over and then be thinking about those prompts as we listen to our presenters today. And then as we go into the breakout sessions, each of the different speakers, along with some of the organizers of this session, will be in each of those breakouts, and we'll be able to have a smaller conversation about some of the topics that we'd like to cover today. Let me just share my screen real quick. I want to do a quick plug for the ESDSWG Community Development Best Practices Working Group. Part of the reason that I'm particularly interested in this session and sort of the initial genesis of one of the sessions for this talk today was to help seed information for this community development best practices guide that we're working on. So this is sort of an extension of a NASA document that outlines some of the tooling and open source software best practices, and this is going to be an extension of that to go into, okay, now that we've got our open source software product out there, how do we build a strong community around that, and how do we maintain that community going forward, so that this the work that we've done doesn't just sort of go sit on a shelf. And sort of building on top of that, we also want to include the overlap, the sort of Venn diagram of the community development needs that are prevalent in the open science side of the house and the open source software side of the house, so that we can kind of share best practices there, and then also have a conversation about where those two communities might diverge and might have unique needs that could be addressed here. So if you're interested in being involved in this, please let me know. There's a link here on the slide, and I'll post it in chat as well, about the work that we're doing. It's all hosted openly. And it's open for contribution. And so, like I said, if you're interested in that, you can get in touch with me outside of this session. So I think with that, we can go ahead and kick off our first speaker, which is going to be Annie, and she's going to be speaking about Geoweaver. So take it away, Annie.
All right, can everyone hear me okay? All right,
yeah,
I hear some nods. Okay, great. Now I'm doing my hosting responsibilities while this, so I've got to remember. Okay, I'm going to spotlight my video. Okay, well, good morning, everyone. And before I start, Sarah, feel free to ping me or just unmute yourself and say stop if I'm going over time, because I'm not with it enough to have a timer going on my screen as well. So don't feel shy to unmute. All right, well, good morning, everyone. My name is Annie Burgess, and I am part of the team developing Geoweaver. Geoweaver is currently funded NASA Access Project led by Jensen's son, who is on today's call and can certainly answer any questions you may have as I'm working through this presentation. I'm going to really focus on the community development story of Geoweaver over a deep dive into the technology itself. Okay, all right. So that being said, I would like to start things off by sharing our value proposition, which actually has recently been updated after numerous conversations at AGU with those in the workflow community pointed out what they saw was unique about our project related to other workflow management solutions. And so our value proposition is that Geoweaver helps researchers manage distributed AI workflows without additional coding, while promoting reuse and reproducibility of those workflows through the preservation of all model run history. And so, like many pieces of science software, Geo grew out of a common challenge amongst a group of colleagues that was really not being solved with currently available software solutions. So as you can see above from this excerpt from their original ESIP lab proposal in 2018, it reads that deep neural networks often run on distributed high-performance platforms to condense the long-lasting duration of training or testing. However, in spatial data-related applications, it is a daunting challenge to manage disparate spatial data storage and compute and dock the pre- or post-processing steps with the neural network. So after the proposal was funded, Jensen and the development team started to build this software and assume the roles of both the core developers and the initial users. And just to kind of get a sense of who's in the room and an opportunity to share, I would ask anyone here to add a +1 to chat, maybe if this sort of origin story is relatable. And by that, I mean common challenge for you as an individual or a group of colleagues, and then you started a project where you were both the core user and the core developer. So a +1, or go ahead and just share your story, but I think those are really interesting and can often help let me know where everyone's at. So as this core group of developers began to build out Geoweaver, beyond knowing it would help them manage their own complex AI workflows, which could be described at a minimum as daunting. At a much broader scale, they believe Geoweaver could really address some of the broader challenges within the field. And by that, I'm referring to really to transparency and reproducibility of AI workflows. So by packaging the code, references to the data, every parameter and overall workflow into a single zip file, Geoweaver makes any AI project easily shareable and reproducible. And that again gets back to kind of what our core value proposition is. So this component of Geoweaver has really always been central to the software, even in the very prototype phase. And as Geoweaver has transitioned from more of an individual solution to one that is intended for broader community use, we find ourselves wrestling with sort of a common misconception that building community around open source software means constantly asking for lots of external development help. And while increasing core developers can most certainly be helpful, development of community for open source software in the prototype phase isn't necessarily focused on expanding the number of core developers on a project. And some of you might wildly disagree with me on that statement, but I'm speaking to kind of where we're coming from. And again, feel free to drop in chat if you agree or sportingly disagree with that sort of statement, but I'll speak a little bit more to it. So rather than that call for really wanting more and more developers, and again, I'm talking about at this early prototype stage of the software, we have focused on learning about how the challenges, or more learning about the challenges of managing and sharing full stack workflows play out in other domains, And we have formed collaborations based around applying Geoweaver to those specific use cases. So by focusing on broadening community in this way, we're working with colleagues far outside of our initial domains, which has pushed us to develop Geoweaver for those use cases which are far beyond our own, leading to greatly expanded functionality. This has also led to a broader potential community of end users, but all the while still having a product that serves our internal goals. So currently, just as you can see on this slide, we're working with teams to use Geoweaver on their own projects related to emissions estimation, snow covered area mapping, and ozone modeling. So over the next year, we'll be seeking out additional use cases through a request for proposal mechanism through the ESIP lab, which is the kind of something I'll be directly leading. We'll support 3 to 5 projects across different domains as they use Geoweaver in their own research. During this time, we'll have regular communication with those projects related to what's working, what isn't, and we will do our best to be super responsive to any posted issues. And I should have, I see Chris is on this call. I'm trying to take a lesson from Chris Linus's recommendation on putting the point you want to make on a slide as the heading. So again, that during this phase of community building and getting those core users, we really want to focus on that super responsive issue fixes and update for early adopters. So I'm just reemphasizing that point there. So again, moving forward, we really see successful community building for our project, not over, again, that focus on a constant call for more core developers, but more on broadly continuing to listen to other domains and what their challenges are, to lean into the ethos of open science. We want to continue to be an active participant in the AI and workflow communities, listen to those that are already using our software and what can be improved. We think it's critically important to participate in other open source communities and other open science communities and learn from them. And we'll continue to seek opportunities to teach others about Geoweaver. Beyond building community around the people that are specifically using Geoweaver to develop workflows, we also see an opportunity of community building in those that are using the outputs of Geoweaver. So if a researcher is able to compose a workflow in Geoweaver, package that zip file, and others are able to open it and then use that workflow to create their own science, we see the scientific output a couple places removed from Geoweaver as additional spaces that we want to know about and that we see as really interesting ways to continue to engage the community. And notice I'm shaking because my office is freezing. If you hear me, this is not a nervous tick. I'm like rubbing my hands together here. Okay. So lastly, I'd like to share this review article that was just published and is a joint effort by the ESIP Cloud Computing Cluster and the ESDSWG Machine Learning Capacity Building Working Group. Jensen Sun, who is a lead PI on Geoweaver, led this article, but really broadly, I think it's just a great example of a community effort on top of an impressive wrangling of content and authors. And Jensen, if you want to drop the link in chat, or I could drop the link in chat after this, I'd be happy to do that. But just a really keen example of a community effort and something that I think will further community building around this topic. So with that, I really think that all of the phases of development and open source software have inroads for developing community, be that bringing on developers, having people share feedback on successes and failures of what they've experienced. And with that, I guess we'll probably take questions at the end, but I will say thank you and pass it on to our next speaker.
Our next speaker is Hamed with ML Hub.
One 1 second, I share my screen. Yeah, you should be able to see my slides now. Good.
Yeah, they look good.
Okay, perfect. Thank you. Hello, everyone. So my name is Hamid Al Mohammed. I'm with Radiant Earth Foundation. And today I'm going to talk about our work in terms of open source standards and communities to help advance geospatial ML. And it's good to talk right after Geoweaver because Annie laid the groundwork for me. Thank you for doing that. So just one slide about Radiant Earth for those of you who might be new to our organization. We are a nonprofit organization, and our mission is really focused on building open libraries of training data and models that would help the global community, particularly to address many global challenges from climate change, from agriculture, and many that you can speak of because geospatial data is horizontal, so it addresses many of those sectors. Our motivation can be summarized in this slide, which is from a workshop we hosted with the NASA ESDS team back in January 2020, about 2 years ago, talking about what are the challenges and advances in the ML for Earth science space. And one of the two of the three, I would say, priorities that came out of those discussions is, first of all, in the training data space, which is the core piece of machine learning applications. You're always learning from the data. We lack benchmarks in our community. We don't have open access and a standard way of, first of all, accessing existing data, and secondly, we don't put enough efforts into producing and generating those data. The second pillar was about how can we better document and share our work. I mean, Annie was just talking about the pipeline of ML, but even on the data side itself, we are not doing a good job as a community. And this has been around for many years. So we at Radiant started, even before this workshop, working on how can we better use existing community resources and gathering more those of kind of like-minded people who are interested in solving this problem to building an ecosystem and repository for doing this. And that's how ML Hub was born. So Radiant ML Hub is basically an open access repository of geospatial training data, and as of a month ago, models. Meaning that you can go to the ML Hub and search for existing training data sets and models that someone else has developed and published with open access, and then start consuming that data. This is just a visual interface of how the website works. You can basically land on a map, see where are all the data sets, look at the different kind of entries, select those that are relevant to you, filter by like tags and keywords, and then when you land on a specific dataset page, you see everything from documentation, from description, DOI, citation, even a basically snippet of code, how to use our Python client and access the data. But how we did this is the part of the community that I want to discuss in the second part of basically this talk. But if you're interested, you can explore the content of this on mlhub.earth. So as an organization, we have three pillars of work. One is the hub itself that I talked about. The second is really the community, and the third is education and capacity development, which is beyond necessarily the community, which is everybody who is interested in our work. In the community pillar, we do multiple things. One is we convene different stakeholders and users to discuss existing challenges and find solutions and best practices, whether this is about, oh, how can we build the API and catalog them for ML-specific datasets, or it's about we want to build a land cover training dataset. This is what we did in 2018. And it is using Sentinel-2 data, for example. What is the specification of that data that would address the users and the community's requirements, basically? And ensuring that there is some level of what we call interoperability among different ecosystems and platforms, because we don't want to have just a standard in addition to the existing ones. We don't want to add to the complexity of the puzzle. We want to make sure we use all of the existing things and then address any failures or any challenges. This is how we started the Stack ecosystem, or Spatiotemporal Asset Catalog, and this is actually a precursor to ML Hub. About 4 years ago, among many conversations with different collaborators and partners, we landed on, oh, there is a problem for discovering geospatial data. We can't have, as of that time, a single specification for catalogs and APIs that you would go to and search for, oh, this is the region I'm interested in, this is the time, and this is basically, I don't know, cloud cover or any other property of existing geospatial data. So we gathered the community who were interested in solving this problem. We identified the problem. We gathered the right people. And then we started working on that as an open source community. Everybody contributed to that, different stakeholders and organizations. But again, it was finding the right and shared problem and interest and getting together. And now that Stack community is kind of among more than 25 organizations, many contributors and users. And it's now being adopted by many of the people because almost everybody had a voice in development of that. And that is what actually is empowering ML Hub. So there are two extensions in a Stack. One is for label data, how you would host and catalog geospatial label data. And the second one, which is very recent actually, is about how you would describe a machine learning model on a catalog and then put it in an API so people can access it. If you're interested, Stack has its own, again, community. We are part of that. We steward that community, but it has 24 organizations other than Radian that is contributing to that. And I will mention at the end what we learned through this experience, basically. Since I'm talking about the community, it's good to see some faces. These are the people who have been working on various aspects of these standards and specifications. The top one is from the recent ML model catalog. We are all virtual, unfortunately. Back in 2019, down this slide, we had the joint sprint with the OGC community, actually. So this is where I want to finish the talk, basically. What did we learn and how we approach this community development and open, basically, specification? First of all, I emphasize that we should build with the community, not for the community. In the sense that from the early stages of the problem development to the actual implementation, to the testing, to the deployment, you're engaging the community. The community can be end users who have no engagement in the actual development, or they can be the actual I don't know, software developers or any other like technical development. So we are always engaging with them. Even when we were building our Python client, we had many multiple one-on-one kind of user interviews and designs to make sure it is the right, basically, purpose and it's addressing their requirements. The second thing is, as I mentioned in the Stack, define the problem explicitly. You want to make sure it is a very explicit and narrow problem. You're not tackling too many things, just, oh, there is something not working. No. What is that failure point? And why existing systems or standards or software is not addressing that? The third piece is the right people. You want to have the right skills in the room to brainstorm about solution and kind of development. In the case of the Stack and the work with it, we needed hands-on people because we're talking about catalogs, APIs, data access points. So we focused on bringing developers, software engineers who were really in that ecosystem and had felt the pain point, basically. But they were diverse in terms of background and kind of organizations and everything. But they're hands-on, so they know the problem firsthand. The other piece is be flexible to change. If you start developing something, it is not just about, oh, since we decided this thing, we should move forward with that. No, if you hear from the community, or particularly the user community, that, hey, this is not working, we are trying it out, be flexible to changing that. And that's how the whole Agile, basically, development works. But we really tested this through this community development. The other piece is keep the core simple. Your community is going to be diverse, particularly, again, both the user community and the developers. They have different requirements. Sometimes it's easier to have a core that is simple, that is shared across everybody. It has a common denominator across everyone, and then add complexities or extensions as more requirements come in. Balance the development pace. Sometimes you need to speed up, sometimes you need to kind of slow down. It is not a continuous development, particularly if you're working with open source community. Everybody has their own level of commitment and engagement, so we should be patient. That's the other piece of the working with the open source community. And last but not least is design, try, and redesign. We went through a lot of iterations, both on the Stack specification itself and the architecture of ML Hub. All of that because we learned through experience what are the things that work, what are those that don't work. And again, we engage the community through all the steps to see how it works. They have had different levels of engagement with us, but it could have been different as well. We could have engaged them more in the development or on the testing side, but we have done the best we could have done on different aspects of it. So that flexibility is key in working with open source community that we learned, definitely. And I want to acknowledge all different organizations that have worked with us, and we have been fortunate to be able to work with them throughout the years to come to where we are with ML Hub and the Stack. And with that, I would also acknowledge funding from various programs and foundations, including NASA Access. We have a 3-year grant that we are working on expansion of ML Hub and ML models. And yeah, looking forward to discussions and questions. Thank you.
Okay, we don't really have time for questions, but you can put questions in chat. And then we'll have questions at the end. Joe, you're next.
And Sarah, this is Jeff. I just want to say I'm keeping track of the questions that are coming through in chat and throwing them in the Google document, so we could either get to them in breakouts or at the end if we have time. So trying to keep track of all those for everybody as well.
Great.
All right, is my audio live?
Your audio is live.
Cool. All right. Well, hi everyone. Yeah, so my name's Joe Hammond, and I'm going to talk about the Pangea project and the community development process that we've been working on over the last few years. And it's actually been it's been fun to kind of take a step back and think about what the process of community development that we've approached the project with and how it's worked, and and I'll even highlight a few places where things haven't gone quite as well. So if you don't know about the Pangea project, it's a project that started about 6 years ago, really to address 3 kind of core problems that we're facing the research community. The first is big data. And so there's this graph here on the right showing the NASA Earth observation data system archive size growing in the petabytes up to 250 petabytes just a few years from now. But we also identified that there's a kind of a growing technology gap between the kind of resources that academic and nonprofit research groups have and industry. And finally, reproducibility. And I think everyone here probably has heard lots of talk about how there's a reproducibility challenge facing many of us. So in steps Pangea, and Pangea really is 3 things at once. It's a community that is promoting open, reproducible, and scalable science. It's an ecosystem of software tools, and it's a platform for doing big data computing. And I'm going to talk about how all 3 of those kind of developed in parallel and how things have gone. So here's a timeline. This slide started out as a brief history, and then things kept getting added, but I'll move quickly through it. So it really just focusing on the gray boxes for a moment. We've really kind of had, how I'm describing it, as kind of five phases of the project. And it started even before 2016, when there was an ecosystem of open source projects that weren't particularly well integrated, but there was a lot of potential there. And so that's, for us, that was the open source scientific Python ecosystem, and that really laid the foundation for the Pangea project. We had an in-person meeting like we did in the before times, where we got together at Columbia University, and that's where the Pangea project was born. And a proposal came out of that to NSF's EarthCube program. And the combination of those like early foundation times and this grant that ended up being funded is really kind of the most rapid technology development. It was fertile ground for solving the core problems that I identified in the previous slide. From there, we started scaling out the project to beta users, and we really just focused on user adoption for a couple of years. And as I'll show in a bit here, we took the project on the road and shared it with a lot of people. And finally, as we get closer to today, we're thinking about new directions and how the project continues to iterate. Speaking of iterating, the development model that Pangea has employed is this, just like Ahmed mentioned, this agile development model where we iterate quickly between scientific users and use cases, software solutions, and then infrastructure solutions. And I think one of the key successes to the Pangea project over the last 5 or 6 years has been the speed at which we're able to iterate back and forth through this cycle. And we really depend on the science users to define the motivations, the science questions, and the challenges that they're running into. And then we've managed to pair science users and developers really closely in a way that allows for kind of bi-directional communication on what those challenges are and what solutions could be present or possible. almost by happenstance, we started developing the Pangea cloud infrastructure. But the ability to build our own infrastructure and find new applications for technological solutions that met science needs was a very key part of all of this. Probably the most central part of the Pangea community is that it's based on the internet, and it started out on GitHub, and there were mostly developers in the beginning that were also scientists trying to find ways of stringing software together to do their research. And so GitHub became the central nexus of the Pangea community. As we transitioned the project towards more and more science users and less software developer focused, we've added a forum, in this case, discourse.pangeo.io, which is really a place where a lot of science users can go and ask questions and engage in a slightly less technical space than GitHub. But in both cases, online open discussions that kind of span a pretty wide range of technical capacities has been a really key part of communicating what the project's up to. In our first proposal to NSF, we had this diagram, which was our kind of wire diagram for what the Pangea architecture would be. And the basic idea is that we wanted to develop a ecosystem that integrated distributed computing, distributed storage, and interactive browser-based computing through Jupyter notebooks. And so I think most people here have heard about this, but the point was this was the kind of foundational wiring diagram. And the goal was to connect the dots, which required a lot of technological solutions, but then also connect the dots to science applications. And that's where we spent a lot of time over in the first few years. When I said we took the Pangea project on the road, what I meant was we went to events like ESIP back in 2018. This is a talk by Ryan Abernathy and Matt Rocklin at the ESIP winter meeting. And there actually are 75 of these in those from those first couple of years, where people were talking about Pangea, doing demos, tutorials, and workshops that were using Pangea infrastructure. And this really led to the Pangea project growing in its applications and its user base. But it also led to a lot of pain points. And I didn't have enough, there's no way I could fit enough GitHub issues on here to fully tell this story, but I thought this was an interesting set of GitHub issues to highlight. As once we had these educational events going and people started using the Pangea infrastructure in the approach of connecting the software libraries that we were working on, we started finding that users had problems, and that was good because it gave us more things to work on, and it also stressed our system of development. So here's just a few. There's technical problems, like people can't access our service. There's application problems, like I'm struggling to parallelize this analysis that I'm trying to do. And then there's a bunch of performance problems about just like doing new things, finding it slow, frustrating use cases. And then finally, and I'll come back to this in a second, there's this last issue, which is like trying to find a way to move data to the cloud, which turns out to be one of those things that we've been bumping our heads up against for at least 4 years, but and maybe longer. So as the project started to grow, we identified new areas of kind of new pain points, and that really fits back into the development model. As people are starting to use the project, we iterate again and we find new solutions that are a combination of infrastructure and software. So where Pangea is at today is that there's actually a kind of a collection. It's kind of growing out in a few directions. There's the Pangea Forge project, which is developing recipes for democratizing data production for analysis ready and cloud optimized data. We have a weekly showcase called the Pangea Showcase. It's a webinar series And it's open to anyone that wants to hear about either development or science applications in the Pangea project. We've transitioned a lot of our infrastructure operations to a nonprofit called 2i2c. And that has really lightened the load on developers that we're turning into DevOps engineers. There's a few educational efforts going on, developing educational content to help onboard science users. And Project Pythia at NCAR and other institutions is leading that effort. You know, 2 more projects that there's quite a bit of work happening on domain-specific tooling now that some of the foundational issues have been addressed. Many folks have turned to supporting advanced kind of scientific analysis, and so smaller packages that fit a more niche application. And then finally, I'm working on a NASA Access funded grant to work on machine learning in the Pangea ecosystem, and that's another application area. So I'm almost at time, so I'll basically stop here. But I think one of the what Pangea has done well is basically motivate development with real world problems, and then tightly collaborate between scientists and developers. And we've, I think one of the most key things that we've done right is we've communicated openly and we've shared what we're working on broadly. So I just ran over time, so I'll stop there, but thanks all for listening.
Thanks, Joe. Our next speaker is Paul Montesano.
Yes, hi everybody. Let me just share my screen.
Looks great.
Paul, you're muted.
Look towards the top of your screen, Paul.
Yeah, I got it. Sorry.
Okay, awesome. Hope you somehow become muted again, Paul. Let me see if I can unmute you. Just a second. If you share, I could likely, let's see. Oh, nope, I can't unmute you.
So is it possible for someone else to share my slides and
Sure.
proceed?
Yeah, I will pull up your slides. Give me 1 second.
That's a fun new Zoom bug, Paul. So if it auto mutes you when you share.
Yeah, that's awesome. It didn't happen before. I'm using it from the browser because this is a NASA computer and we can't download the Zoom app.
Gotcha. Yep. All right.
All right. Am I going to have the same issue since I'm on a NASA computer? Let's see.
But you don't need to be unmuted, Sarah. So you should be able to share and Paul can be unmuted.
Yeah.
So we can see your screen.
You can see. Okay. All right. Put it on slideshow.
And we can see, we're seeing the Zoom browser. So you might have to share your other monitor or if you have it somewhere else.
Stop sharing. Share that one. Better?
Yep.
Okay, thank you very much.
Okay.
Thank you. So everybody knows my name by now. And I'm talking about the MAP, the Multi-Mission Algorithm and Analysis Platform. So I'm a research scientist at NASA Goddard Space Flight Center. And so I'm going to be talking about this platform from this perspective of a scientist who's a new user to the platform, or at least I was at the start of this project. And as a scientist who uses geospatial data to study patterns of boreal forest structure. And so this is kind of an explanation of this sort of open science platform from the perspective of somebody who's trying to assist the PI, Laura Duncanson, and the other co-Is on this project to sort of achieve project goals. And this is a project that's funded underneath NASA's Arctic Boreal Vulnerability Experiment. And so from my perspective, one way to think about why this platform is important is because that there are significant uncertainties that exist in the best answers that we have now to some fundamental science questions. And so one example of that, so next slide, please. One example of that is the global carbon budget, where science's best estimates of our CO2 emissions don't exactly equal our estimates of where that CO2 is ending up. And so, big data platforms like the map are kind of set up to be able to bring a lot of data in from a variety of sources in greater detail than perhaps what was available before, and begin to address some of these uncertainties. And so this is where our project fits in, which looks at biomass density in the boreal forest in high detail across its circumpolar domain. So next slide, please. So what is the map? This multi-mission algorithm and analysis platform. It's this bilateral platform between ESA, and the European Space Agency, and NASA, and it's designed for this type of collaborative science. And where scientists come in and they sort of develop their algorithms and test them, create their products, create their estimates, and then publish those results. It's an example of a cloud compute platform. It's on AWS. And it hosts a lot of these new, very large spaceborne data sets, some existing now, some soon to exist, and also ancillary data and other reference data. And it's attached to these S3 buckets where other spaceborne data sets are archived. So it allows you to bring a lot of data together in a sort of data fusion approach. And these large compute platforms help address the uncertainties in these fundamental questions, like the one I just sort of talked about before. Because again, we can bring in a large volume of complementary data across very large geographic domains. Next, please. So what does map look like? Again, this is an explanation of what map looked like from my perspective as just a relatively new user to the system. So the map is it's this platform that sits in AWS, and from my perspective, we have basically access to S3 buckets of maps, archive of Earth data, as well as curated user output. And then we can access that data through the Earth data search that we can access through a Jupyter Hub code environment, code development environment. Then there is also these batch processing capabilities, and all that is accessible from these shared workspace environments that are running in these in Eclipse Che development environments. So really what this allows me as a scientist to do is work with my co-investigators really on the same virtual computer in the same notebooks at the same time. And this is just one entry point into an AWS cloud compute environment in general. Next, please. So on a platform like this, our goal is to, obviously do what we said we were going to do in our proposal, but that involves this sort of iterative modeling, mapping, reporting, and then updating those results as we move through this project. And a big platform that brings, co-Is together in the same sort of virtual workspace is tuned for that. So, what we're looking at here is just a map of our attempt at displaying a large amount of a portion of the data that we're using for this project. And this is sort of a kind of an important step in being able to then clean this data and model it and use it to create estimates of biomass density across our domain of interest. And so this modeling and mapping of above ground biomass in the circumpolar boreal forest is our goal. We're using ISAT-2 data, that's canopy height estimates, to train models that then apply these models to gridded estimates or gridded values from Landsat and other topographic variables. And then, we're learning how to adapt these models spatially to refine our estimates. And in terms of reporting our results, we're able to use these, familiar code environments, Python and R, and create these fully reproducible workflows that can be updated as new data sets or new versions of the data come in. And we can also report fairly clearly the versions of our output. And one example of this was this past fall, we created a preliminary data set of our biomass density map across the boreal for the COP26 conference. Next, please. So our ISAT-2 data set is one of the main data sets that we're using to do this. And again, this requires a lot of data cleaning and preparation and filtering of the data to be able to return the type of training data set that we think we need to produce our best estimates. And this is an iterative process. There are millions of filtered data points for each year of this, of our sort of temporal study domain. But before that, there are, an order of magnitude more observations than that. And so a massive compute platform allows us to use these big data sets and wrangle them into a position that is useful for us. Next, please. And a platform like this helps accomplish what we talk about a lot in geospatial science, data fusion and data integration. There are a lot of ways to do this, and we think we're integrating some important complementary data sets in a useful way to return the type of biomass density estimates that we want. These data are not in the same location through the maps search utilities, and because it's on AWS, we're able to bring in data sets from different locations and combine them in ways that would be otherwise, from my experience, very, very difficult. So here we link our ISAT-2 observations with Landsat composites that we build on the platform. Next, please. And we do something similar with in another data set. In this case, it's a topography data set from the Copernicus DEM. So we're bringing a variety of disparate data sets together across broad scales in relatively fine detail. Next, please. And one way we've realized that we're going to succeed in this project is by taking this tiled approach to our biomass estimates. And this takes advantage of a system like this, the parallel processing abilities of a system like this. And so by tiling our data, we're not only making use of the map resources in terms of compute, but we're also able to optimize, we think, our estimates of biomass in the first place, because we can size these tiles in an appropriate way to make use of each particular virtual machine's resources. We can run those models many times per tile and achieve more robust estimates of uncertainty in our output. And so, we think a tiled approach like this, from our perspective, is really kind of what a system like the map is designed for and supports well. Next, please. And of course, we have lots of these tiles across our broad domain. So, over 4,000 individual tiles where we're integrating this variety of spaceborne data to produce our biomass estimates. So again, this is a massive project for many of us who are co-Is here. We're new to it, but we're able to use this type of system in a way that makes sense for achieving our specific science goals because of the relative usability of this Jupyter Hub environment sitting on top of the AWS ecosystem. Next, please. So at the end of the day, we get estimates by tile of forest biomass density, as well as uncertainty. We kick these estimates out at 30-meter resolution for the circa 2020 time period. And we produce these cloud optimized outputs that have a variety of uses. And one of those uses is internally to be able to kind of assess how well are doing, tune our models and iterate over that workflow. And another one of those uses is to be able to then show our preliminary results to interested parties through some sort of visualization dashboard. Next, please. And so these visualization tools that are available on the map and other similar open source platforms are actually a very big part of our workflow. And from the perspective of a scientist, very sort of critical to improving our results. We can take a first pass at looking at where our estimates seem to be succeeding and where they're clearly failing. And we can really figure out how to tune our workflow in the right way. So we can accomplish a lot of the tuning just simply by looking at this vast amount of data that we produce right off the bat in sort of initial runs. So it's these visualization tools that are really supported by this type of platform that are, for me, have been incredibly helpful. Next, please. And so you can check out this link here to observe, to view our preliminary map that we published this fall, not published, but released. And to summarize here what I've been talking about, this map system, again, from my perspective as a scientist, really seems to help get at some important science questions that require analysis of detailed data across broad geographic extents, provides tools for discovery and processing and analysis and visualization of these large data sets, features a development environment that's designed for collaboration and collaborative open science, and it facilitates data integration or data fusion, bringing lots of different data sets together in a unique way to improve estimates of, in our case, biomass density. So it's a well-developed example of a comprehensive geoscience platform on AWS, and it's just one entry point into the cloud compute environment. Thank you.
Thanks. Alexi, you're up next.
Great, thank you. Can you, I'm assuming everyone can see and hear me. If not, just give me a shout.
Yeah.
All right, so my name is Alexi Shuklanov. I'm a research scientist at NASA Goddard. We're a little bit behind time here, so I'll try to make up some time with this presentation, which hopefully should be easy because a lot of the content really has already been presented. And there's just a few additional pieces I want to add. Before that, I want to acknowledge that this is really the work of a team of probably a couple dozen people. Some of the leads are highlighted here: Doug Borton, Sujay Kumar, Dennis Felix, and Chris Peters-Ladard, Dalia Kirschenblatt. But this is really a large team effort, this NASA Earth Information System. So the background here is that if you look back at the decadal survey, which largely guides a lot of the Earth science activities that NASA undertakes, there's this quote in there that talks about the importance of combining information from a range of sources, including field campaigns, lab experiments, models, theoretical studies, and again also talks about integrating information from several approaches, and this leads to these insights that go beyond the sum of their individual parts. And this is really what's motivating, I think, this particular project, is this quote from the decadal survey. And so if you look at some of the decadal survey questions, though, they're formulated around very specific science topics. For example, what processes determine the spatial temporal patterns of air pollutants? How is the water cycle changing, and how do these changes affect the frequency and magnitude of extremes, such as droughts and floods? And how will local sea level change along coastlines around the world in the next decade to century? And so these are really nice questions if you're a scientist, but if you're a normal person, right, what you really care about is how likely is it that my neighborhood in the next week will end up looking like this because of air pollution? Or what is the likelihood that my crops will dry out? And what should I do if that happens? Or what is the likelihood that something like this will happen again to my community, like this flood in Annapolis? And so what these, the point here is that these decadal survey questions need clear, actionable answers that people can understand and people can respond to. And so NASA has, I think, the tools, and I'm going to toot our own horn a little bit here to address a lot of these things. I mean, we have world-class modeling and data simulation capabilities, what's shown here is the GEOS model. We have science expertise. Here is Leslie Ott from our own Goddard Space Flight Center presenting to Kamala Harris just a couple of months ago. We have world-class engineering, of course. We build fantastic satellites and other kinds of instruments. We're also global pioneers, I think, in data distribution and stewardship. And finally, we have really robust programs for applications and stakeholder engagements. So we have all the pieces that we need to be able to do this. And now we just need to get them all to properly sort of fit together in the service of these kind of decadal survey objectives. And at the same time as all of this is happening, we also have all of this push for open science. There's a bunch of open science initiatives, including NASA's Transition to Open Science initiatives, or TOPS. There's the growing data volume and complexity of observations, including particularly from the Earth System Observatory, which is the next set of big satellite missions that NASA is going to launch in the coming decade. And finally, there are all these opportunities in cloud computing coming around that you've heard a lot about before, so I don't really have to reiterate here. And so I think collectively there is opportunity to pull all these things together and create, for scientists, these scientific collaborative analysis environments, such as MAPA and some of the other things that we've heard about already. If you're a stakeholder, there's opportunities to just sort of create these interactive dashboards. This is what you're really after if you want to make decisions. And if you're the public, you don't even necessarily need dashboards. What you care about are these data-driven, data-informed narratives. For instance, what's shown here. And so that's really what the EIS struck out to try to do. And we conducted 3 pilot studies over the course of 6 months, starting in basically March of last year and concluding in September. One was on fires, one was on freshwater, one was on sea level change. Their theme statements, sort of their big selling pitches, are stated here. But I'll jump straight to the common themes. First, they tackled complex Earth science decadal survey questions using state-of-the-art models and observations from NASA and its partners. We developed our own open source scientific collaboration environment, building on a lot of the tools that were already shown today. And also, we translated scientific results into actionable information that people could actually use. So a quick survey of these pilot studies. This is NASA Fire. I think the biggest highlight here is actually, so what's happening in this little interactive diagram is each orange dot here is an individual active fire detection from a satellite, which is of course useful, but it's even more useful on a map like this, which is showing you the evolution of that fire day by day and the locations of the active fire perimeter and total burned area by that time. So this is really a nice, more interesting, I think, view of the fire and its spread that is actually more relevant to someone that cares about what's going to happen next to that fire. And I'll also highlight that these time series here that are shown on the right actually comprise data that's coming from at least 4 different data portals, right? The GOES data comes from NOAA, the MODIS data comes from LPDAC, the VIRS data comes from LADS. And the fire weather indices are actually custom things that are generated by our Goddard Institute for Space Sciences. But you really want to be able to do analysis like this. You want to have all this data in one place. So that was the fire study. One of the things that the fire study did anyway. The sea level team had this interesting theme of from the Greenland ice sheet to your backyard, and looked at really the local impacts of the Greenland ice sheet melting and potentially melting in the future, and what are its local, hyper-local level sea level change impacts. And so we combine information about combined models running in the cloud of how the Greenland ice sheet is actually thawing. So here you have 2 different model projections, model estimates shown here on the left in a nice Jupyter notebook. And on the right, a nice story map that highlights the vertical land motion at the hyperlocal level of Hampton, North Virginia. That's showing you what are sort of the hotspot levels for sea level change in this particular area at the neighborhood block level, right? So again, from sort of scientific information to actually useful information to people. Excuse me. And finally, the freshwater team did a whole bunch of different things. This is one case study that I really like to highlight. That again, sort of similarly to fire, shows you that to really understand a single extreme precipitation event, you need to integrate a lot of different sources of information. So in this case, you're looking at the Midwest floods in 2019. That combined information from our land information system, from the Global Precipitation Mission GPM, from SMAP, a soil moisture sensor, planting delays that are captured by MODIS, all of these different instruments, all of these different kinds of observations combined together to tell a single story of this sort of worst of all worlds event, which had high rainfall, rapid snowmelt, record flooding, really wet soils, and finally that led to delayed planting. So The thing that made all this stuff possible really is all of us sort of working together as these teams in the cloud, scientists working with software engineers together and scientists from different disciplines collaborating, and all of our data in one place with our compute. You've heard all of this already from the lovely talks that were presented earlier. Especially, I want to give a shout out to the Pangea team, which basically made this project possible to pull off in just a matter of 6 months. And so I highlight a few of the sort of highlights here. That said, that for this project, for the sake of 6 months, we sort of spun this up ourselves, which again was possible because of the hard work that teams like Pangea have put in to making these tools extremely usable, extremely easy to set up, extremely easy to configure and work nicely together. But I think moving forward, I'm glad that Paul actually presented right before me, because NASA has more mature versions of this exact stack, particularly in its map platform. And so I think that the future of the Earth Information System is actually to take these same science teams that we've already assembled, these stakeholders that we've already identified and talked to and formed relationships with, and move them onto that more mature platform, which is MAP, and really scale that out. So that we have a single platform rather than 3, as we have right now with these EAS projects. And so I'm going to stop there. This is, again, sort of the takeaway slide for the 3 things that these projects accomplished. And I look forward to discussing this with all of you in the breakouts. Thank you.
Great. Thanks, Alexi. So next, we're going to go to breakouts. And we have 4 breakout rooms, and people will be randomly assigned. However, if you are a speaker, you can put yourself in a breakout room. And so Jeff and Hamed, I would like you to go to breakout room 1, Joe and Elena to breakout room 2, Paul and Annie to breakout room 3, and Alexi and I will do breakout room 4.
And just to clarify for the speakers, you'll be thrown into a breakout room because we're going to do that assign. So if you get thrown into one and that isn't your room because you're a co-host, you can do the hop out and choose your room. So they are all open now. Let's see.
And then the questions for the breakout rooms are on the document. Just scroll down until you find the appropriate breakout room. They're all the same questions. So
everyone should get the whiplash pull pretty quick here back to the main room.
Yeah.
Never enough time for those conversations. In planning, I'm always like, oh, this will be plenty of time. We'll probably just be staring at one another by the end of it. And then that's never the case.
Yeah. Okay, so I think we had originally planned to wrap up with presentations from each breakout group. I think maybe we all put our thoughts down on the document, hopefully. So maybe we'll finish up with questions for the speakers. So that gives us about 15 minutes for questions. Anybody? We could start with some of the questions from chat, if you have those, Jeff, or just open it up.
Yeah, I can go through the ones that we have in here. So the first one was for Hamed, ML Hub. How do you design your convenings, e.g. around specific use cases? What facilitates the domain and data scientists communicating to develop new standards?
Yeah, thank you, Ryan, for that question. I tried to put some thoughts in the chat, but happy to elaborate on that. I mean, it depends. Sometimes it's around a use case. For example, we had one specifically around, okay, we want to work on land cover training data sets. We're bringing the community on the land cover side and the ML community discussing about requirements of those. Sometimes it's around specifications and standards like the stack board. In that case, we specifically target that kind of community, and the theme is, okay, this is a problem with the stack. We usually narrow it down to problems, if not one problem, a handful of them, to make sure the focus is there. And the kind of communication is using open channels. So most of these communities have an open way of a forum type of thing. Sometimes it's on Slack, like ML Hub. Sometimes it's on like a forum page and a web page. Sometimes it's a Gitter channel. So there's always a kind of online virtual community that is always communicating and chatting, and it's open to everyone to come in and ask questions and join. So that's how the communication usually happens.
Hamed, what process do you use for engaging with stakeholders? For example, like how do you ensure that you have the right people in the room?
Yeah, so I mean, there are two things in there. One is, so we regularly develop a market map that I put in the chat. So as an organization, we have a good understanding of the players in the sector, and we directly and one-on-one reach out to them and encourage them to engage in those problems. But in addition, because we might miss someone, we always open calls for collaboration and participation on social media, on our email list, and we promote that through our partners as well, to try to bring other voices, other players who are interested to work on that ecosystem. So yeah, it's really that one-on-one and the social media newsletter kind of thing.
Excellent. Does anyone else have any other specific questions for Hamed? Okay, I'm going to move down to the last three here are actually for Paul. What is the intersection of MAP's Earth Data Archive and the data currently populated into the Earth Data Cloud?
The intersection of, I'm sorry, you chopped up for a second.
Oh, that's okay. What is the intersection of MAP's Earth Data Archive and the data currently populated into the Earth Data Cloud?
Oh, well, I mean, it's the map has a small subset of what's in Earth Data. Yeah, and Amy would probably be able to answer that much better, since our project group is kind of is on the user working group, and we're kind of testing out this platform. They've brought into Maps Archive the data that we need specifically for our project. But as far as I know, that most of the data that a wide range of Earth scientists would want might not be there quite yet. But Amy, you might have much more updated information than I do.
Yeah, we're continuously working on building out the data archive for MAP, given what the MAP user scientists need. And so given what they need in data as it's getting frequently updated, there's basically an overlap. There's an overlap really in the data sets from the Earth Data Archive that aren't already in the AWS cloud. So data sets that are already available in the AWS and through NASA's AWS cloud, we're basically supporting sort of token-based authentication for the users to access those data sets. But because we want compute proximate, we want the compute to be proximate with the data that is still on premise at the DACs, we have made some of those data sets available on the AWS cloud specifically for the MAP users. So there is definitely some overlap between what's available at the DACs and what's available in the MAP cloud archive, given that not all, or only a very small subset of Earth Data Archives are available on the AWS cloud at this time. And then in addition to that, there is also a few data sets that we have made available to MAP users that are not available on the Earth Data Cloud. So one of these, for example, that's of high value is the JEDI calibration and validation data set that is produced or collected by the University of Maryland. That's data that is used to calibrate the models from field campaigns, field and airborne campaigns. So we've made that available on the map where it does not yet exist in the Earth Data Archive.
Excellent, thanks. Again, for Paul and maybe possibly the greater MAP team as well, how open is MAP? Can any scientist get on and have a look at the products produced, or is it more like a gated community of known authorized users?
So I think at this point, it's just members of the user working group and then others who have been granted specific access, because there's still a lot of development going on. Amy, do you have anything to add to that?
Yeah, it's mostly for the map user working group, and we're opening it up to a few other mostly like NASA scientists. Actually, Alexi, who spoke earlier, has been looking at using the map as well. So it's mostly for a small subset of users, and we're as part of the NASA Transform to Open Science, sort of initiative, like larger initiative. And Alexi can say more about this too as well, but we're looking at repurposing a lot of the infrastructure, not repurposing, but like reusing a lot about what we've learned about open science infrastructure from the MAP platform for new projects that are more open to a broader public. But I would just asterisk all of this by saying, it's really hard to make some of these open science platforms completely openly available given cost concerns, right? So there has to be some user tracking. There has to be some sort of user tracking in order not to basically have runaway costs.
Thanks. Okay, final question on the map side. Earth data search is a key part of the map workflow. How does a scientist developing in the Jupyter Hub environment use the search? Is it keyword-based, natural question asking? Curious how map makes easier search over diverse data sets.
Yeah, so that's a good question. And I didn't talk about that in the talk, but that's kind of like a key link between what data exists and what data you can get at and work with. And so when we jumped on the map and we joined it at the start of this project, we quickly learned that there was an existing library that the map had, a Python library that the map had built that were basically functions that allowed us to query spatially and temporally for our data sets of interest, query the Earth Data Archive and bring it into and perform that query in a notebook and return a list of basically paths to the data sets that you want to process and work with. So it was that kind of set of Python functions that existed that were there for us that they showed us and taught us how to use. Those were key.
Excellent. So there's another question in the chat. This is to Alexia, though I think he has already dropped. So I don't know if anybody else on the call can answer this. Is Earth Information System already open sourced? Can you share a GitHub link?
I believe it is open sourced. I think
my understanding is that some of the notebooks are open source, but the infrastructure has been is not completely open source. Like it's used some open source libraries, but so it's a complex system, right? So I think it's like yes and no. But yeah, we should ask Alexi.
Did we already get Peter McHarry's question? Any thoughts on the process of granting researchers access to future collaborative science environments? I believe that was posted during Paul and Amy's question earlier.
Is that, I guess, future collaborative environments like map, making them public? Is that what the question is? I think part of the thoughts is that in the future, we will look at the map NEIS technologies for creating more openly available technology. But those plans are in the works now.
And I'd love the conversation to keep going, but we are over time now, and there's a coffee break that starts in just 7 minutes that you could access from Kiko chat. So I have to end this because I've got to start that. So do the conveners have any last notes or anything they'd like to share?
Please join us for the next session, for the next community development session.
And thanks
for
for
the coffee break.
Thanks for participating in this one.
Yeah, thank you, everybody.
Bye, everyone.
All right, see you at 4.